In this video, we're going to cover the most important machine learning algorithms in the shortest possible time, so you can quickly understand how they work and where they're used. From linear and logistic regression to decision trees, random forests, support vector machines, KNN, Naïve Bayes, gradient boosting, k-means, PCA, and more, you'll get the essential foundation of ML in just one crash course. And here's the deal. We're giving you this entire crash course completely free. No paywalls, no hidden fees. But remember, if you don't hit subscribe, like, and share, you risk missing out on the next set of crash courses we're already working on. So take 2 seconds now, subscribe, like, and share, and let's jump straight into the world of machine learning. Have you ever tried to predict house prices based on just looking at characteristics such as location or size? That's what linear regression does. It transforms input variables to a continuous output. It accomplishes this by finding an approximation of a straight line, or in more than 2 dimensions, a hyperplane, that best fit the trend in the data. The general idea is to minimize the difference between the calculated values and the actual outcomes, typically through a process called least squares. For example, using information about the sizes and prices of houses, a linear regression can extrapolate the price of any sized new house. Simple and intuitive to both understand and interpret, but strong in that it provides a standard model to most real-world applications. Your sales forecasting, risk assessment, or even students' grade prediction. But it makes a linear relationship assumption, so that it can be invalidated by complicated nonlinear patterns, but as a beginning, it's priceless. And how does Gmail decide whether or not an email is spam? That's when logistic regression comes in. While linear regression predicts continuous values, logistic regression is used in classification problems with categorical output values, such as yes or no, spam or not spam, fraud or legit. Instead of a straight line, it uses the logistic function or sigmoid curve to rescale predictions between 0 and 1. They are probabilities, so it is easy to assign classes. Imagine a doctor deciding whether or not a patient has an illness based on symptoms. That's exactly what logistic regression does, classifying by probabilities. It's widely used in such applications as credit risk scoring, churn analysis, and sentiment analysis. It's simple, but gives great insights when you need interpretability and fast results. So, it's the go-to for most classification tasks. Did you ever play 20 questions when you narrowed down possibilities by asking yes or no questions? Well, that's exactly how a decision tree works in machine learning. It is a flowchart type model that makes decisions based on partitioning data into branches under some conditions. Every internal node is a feature, every branch is a decision result, and every leaf node is a terminal prediction. For instance, to determine whether an individual will purchase a product, the tree may first inquire about income, then age, then consumer behavior, progressively partitioning down to a choice. The beauty of decision trees is that they are easy to understand and explain, where you can just follow the reasoning path, much like following steps in a flowchart. They find widespread usage in fields like healthcare for disease diagnosis, finance for lending, and marketing for customer segmentation. Decision trees will have the tendency to overfit in that they overfit the training set and subsequently lose on unseen data. To control this, techniques like pruning are used in an attempt to minimize the tree. Despite their limitations, decision trees provide a firm foundation for more advanced ensemble methods such as random forests, which capitalize on their strengths to improve accuracy and stability. Have you ever had more than one friend advise you before making a significant choice? You probably trusted the majority view over an individual response. That is the rationale behind a random forest. Instead of relying on a single decision tree, it produces many trees and averages their result for a more reliable and consistent prediction. Each of those trees is trained on a random subset of data and attributes, which introduces variety and reduces the risk of overfitting. At prediction time, the model aggregates the predictions, majority vote if classification is the task at hand, or average if regression is underway. This combination approach renders the random forest robust tools that can easily handle both structured and unstructured data. They find widespread application in finance to score decisions, in healthcare to predict disease, and in e-commerce to make recommendations. It's the wisdom of the crowd phenomena. Whereas any individual tree may be noisy or biased, averaging many cancels out errors and captures more subtle relationships. The downside is that they are sometimes less interpretable than a single tree, but their high accuracy and robustness make them a first choice in practical applications where stability is most crucial. Arriving at SVMs, a support vector machine is a supervised machine learning model primarily for classification problems. It aims to find the optimal hyperplane that maximally separates data points of various classes. Unlike a simple linear classifier, SVM attempts to maximize the margin, the distance from the boundary hyperplane to the support vectors on it. Maximization will yield a more generalizable and robust decision boundary. When data is not linear separable in the original space, SVM employs the kernel trick to transform data into higher dimensional feature spaces where data can be linearly separated. This flexibility makes SVM most useful in domains such as image recognition, text categorization, and bioinformatics. Although training might be computationally expensive with large datasets, SVMs are valued for their high accuracy and precision in complex tasks of classification. Steering clear of dependence on margin-based models such as SVM, let's examine a straightforward simple model, K nearest neighbors, or KNN. If you're relocating to a new neighborhood and trying to forecast your interests based on the interests of your neighbors, if all your neighbors are gardeners, then chances are you turn into a garden nut as well. This is what KNN does. When a new data point is presented, the algorithm examines the K nearest points in the training data, typically by distance, and predicts the majority label, classification, or mean of their values, regression. KNN never constructs an explicit model at training time. It always relies on the saved data, and thus it is a lazy learner. While simple and efficient with small numbers, it is slow and memory-hungry with big numbers. But its simplicity and ease of comprehension make it an ideal starting point for non-parametric models. Did you ever try to guess whether it would rain today by just observing the sky, temperature, and remembering yesterday's climate? You naturally combined a few clues to make an educated guess. That's exactly what Naïve Bayes does. Based on Bayes' theorem, this algorithm guesses the probability of a class given the input features. The naive name comes from the assumption that all the features are mutually independent, though in practice they are not necessarily so. This simplification aside, Naïve Bayes performs extremely well when independence is at least approximately true. A nice example is spam filtering. The algorithm examines single words such as free, offer, or limited, and determines probabilities of an email being spam when they appear. Despite the fact that the words are not independent, this assumption still generates very strong results. Naïve Bayes is used extensively in text classification, medical diagnosis, and recommendation systems due to its speed, efficiency, and ability to cope with high-dimensional data. Its ease of training on large data and frequent competitive accuracy to complex models is its popularity, though it will fail when there are highly correlated features. Naïve Bayes is a strong, light algorithm in most real-world situations. Ever tried to improve your gameplay by learning from every mistake you made in previous rounds? That is the spirit of gradient boosting machines, GBM, an ensemble technique that builds models in an iterative manner, where each coming model focuses on the rectification of the previous one's errors. While random forest builds trees separately, gradient boosting is about learning from mistakes, with improvement in the accuracy of prediction happening incrementally. Think of it similarly to students taking turns providing responses, each learning from the error of the previous student to creep closer to the correct answer. GBM builds a series of weak learners, typically shallow decision trees, and combines them into a strong model for making predictions. Each tree is trained on the residuals, or differences between predicted and actual values, to enable the next tree to address hard cases to predict. Through iterative correction, the model captures subtle patterns in the data, making it highly valuable for regression and classification. Over time, more optimized versions like XGBoost, Light GBM, and CapBoost have emerged. XGBoost introduces regularization and parallelism to boost the speed and precision. Light GBM uses histogram-based algorithms to cope with massive data seamlessly. And CapBoost deals with categorical features automatically to reduce pre-processing. The libraries are industry favorites, having won data science competitions and powering applications in finance, marketing, and healthcare. Though powerful, gradient boosting must be tuned very carefully, with parameters to avoid overfitting. Nevertheless, the capacity for converting weak models into extremely good predictors render it a must-have tool in contemporary machine learning. Ever tried mastering a skill by focusing on the mistakes you made in previous attempts, gradually getting better with each one? That's the concept behind AdaBoost, the adaptive boosting. Unlike single models that can keep on making the same mistakes, AdaBoost pieces together several weak learners, often just simple decision trees, into a strong model. Each subsequent learner puts additional focus on the points of data misclassified by previous learners. In effect, learning from mistakes. Think of it as a teacher who observes which students perform poorly on specific problems and then adjusts the next lessons so that they can perform better. AdaBoost does the same. The ability to learn from its own mistakes in a self-correcting approach allows AdaBoost to learn incrementally from its errors, maintaining higher overall predictive accuracy. It's particularly wonderful for classification issues like detecting bogus behavior, spam message classification, or predicting customer churn. While it's outlier sensitive and sensitive to noisy data, simplicity and the ability to scale weak models to become strong predictors render it a favorite among ensemble learners. By having numerous weak classifiers combined with the focus on difficult cases, AdaBoost demonstrates the power of small incremental improvement towards robust results in machine learning. Did you ever sort a combination of candies based on color or taste, even though no labels were telling you what type was what? That's exactly what K-means clustering does. It's an unsupervised machine learning algorithm that groups data points into categories based on similarity. The K refers to the number of clusters you want to create, and the algorithm goes ahead to allocate each point to the nearest centroid or cluster center. The centroids are then iteratively adjusted until the clusters converge, minimizing the distance between points within the same group. K-means is applied widely in day-to-day applications, including customer segmentation in marketing, image compression, and document classification. Think of it as organizing your music list into genres without knowing which songs belong in what genre. The algorithm determines it based on clustering songs with the same properties. It is fast, simple, and efficient on large datasets. But its main limitation is that you must specify the number of clusters in advance, and it struggles with irregularly shaped and overlapping clusters. Outside of these challenges, K-means remains one of the most popular clustering algorithms to find concealed patterns in data. Did you ever organize folders and subfolders for your documents? Example being a root folder for work, subfolders for projects, and within those, single documents. That is the idea behind hierarchical clustering, an algorithm that produces a tree of nested clusters. Unlike K-means, you don't have to decide in advance how many clusters there are going to be. Hierarchical clustering either starts with every point as one cluster and merges them step by step, algo-merative algorithm, or starts with one cluster and splits it into smaller ones step by step, divisive algorithm. The result is a dendrogram, a tree-like plot showing how clusters merge or split at each level. This comes in handy if you want to explore the intrinsic hierarchy in your data. For example, for biology, you would be able to categorize species as a function of genetic similarity, while for marketing, you would categorize customers in terms of similarity levels. Ponder creating a family tree of data such that first-degree relatives are grouped, followed by distant relatives, and so on. Though hierarchical clustering can be computationally expensive for large data sets, it presents a robust method of visualizing and interpreting complex data. Ever tried to summarize a long novel into just a few highlights, but still maintain the essence of the story? That's exactly what Principal Component Analysis, PCA, does to data. PCA is a dimension reduction technique that transforms high-dimensional data into fewer variables called principal components, with as much information preserved as possible. It works by finding new axes, or directions, that explains most of the variance in the data and thus highlight the most prominent patterns and ignore noise or redundancy. A way to think about it is to compress a large picture to one with smaller file size, where you lose a bit of detail, but the overall picture remains. PCA. It is widely used in fields like finance to reduce the number of market indicators, in image classification to reduce pixel data dimensionality, and in genomics to analyze genetic variation. Its biggest strength lies in the fact that it makes full, high-dimensional data easy to visualize and interpret by reducing it often to 2 or 3 components for plotting. PCA is robust but makes linear assumptions and may not be able to find complex patterns. Nevertheless, as a tool for data reduction and extraction of structure, PCA is the cornerstone of unsupervised learning. Did you ever have a smoothie and try to guess which fruits were blended into it? Even though the final product looks homogeneous, it's actually a mixture of many ingredients. That's the thinking behind a Gaussian Mixture Model, GMM, a probabilistic method that posits data is drawn from a distribution of multiple Gaussian distributions, each with its own mean and variance. Rather than putting each point strictly into one cluster, GMM assigns probabilities so a point can be part of several clusters to some degree. That makes it more adaptable than hard clustering algorithms such as K-means. For example, in customer segmentation, GMM can identify certain customers as possessing traits of more than a single group, unlike putting them in just one group. The model successfully estimates the parameters of the Gaussian distributions by applying the expectation maximization (EM) algorithm, optimizing them until they best fit. An analogy is having multiple overlapping hills fit into a complicated terrain in which every hill represents a Gaussian distribution. GMM is widely used in speech recognition, anomaly detection, and bioinformatics. While more computationally expensive and under the assumption that the data tends to follow Gaussian patterns, its soft clustering ability is an attractive feature of a general-purpose tool for modeling the complexity of real-world data. Did you ever realize how many everyday technologies are running in the background with machine learning nowadays? From your phone unlocking itself with facial recognition to Netflix recommending your next TV binge, or banks detecting fraud in real time. In the course of this crash course, we've covered the fundamentals of supervised learning methods like linear regression, logistic regression, decision trees, random forest, SVM, KNN, Naïve Bayes, and gradient boosting models, all offering varying ways of predicting and classifying data. We proceeded to unsupervised learning, where we saw clustering models like k-means and hierarchical clustering, dimensionality reduction with PCA, and probabilistic modeling with GMM. Each of these algorithms is strong in areas that the others are weak in and has best suited applications. But together, they form the heart of modern machine learning. The key takeaway is that machine learning isn't about memorizing formulas. It's about choosing the right tool for the right problem. Whether simplifying data, uncovering hidden structures, or making accurate predictions, these algorithms empower us to turn raw information into actionable insights. As technology continues to advance, the role of machine learning will only grow, shaping industries and our daily lives. By understanding these core concepts, you've taken a strong step toward mastering this transformative field.